Nuclear magnetic resonance spectroscopy is a way of analyzing molecules using a parameter that follows Fermi-Dirac statistics. Now, Fermi-Dirac, that is for systems of quantum mechanics, systems of particles with half-integer spins, and two that are relevant for nuclear magnetic resonance will be the electron and the proton, both examples of fermions in our molecules. Now, two effects that we will see in the results of our NMR experiments will be from the electron spin. That will result in a shielding effect observed in our NMR spectra, and the proton or the nuclear spin will result in a coupling effect. Some examples of NMR experiments include Proton NMR using the hydrogen-1 atom or isotope, carbon-13 NMR, of which there are two typical types, broadband decoupled and depth NMR. There is also HSQC for connecting two different spectra. Now, the standard Proton NMR, just looking at the various proton environments throughout a molecule, what we see is essentially along the x-axis or along the axis that's in parts per million, the specific resonance or where along that axis a hydrogen environment shows up, that is the result of the electron spin shielding. Different shielding effects will cause proton environments to show up either further to the right, upfield, or further downfield and to the left to higher parts per million. And another effect that we're seeing is that some of these peaks, some of these resonances have either multiple peaks, and they could be doublets, triplets, quartets, multiplets, singlets. This will be what's often used for vital information. In Proton NMR, this is the coupling effect from the nuclear spin. And the coupling effect essentially for Proton NMR lets us infer for whatever hydrogen environment we are looking at, what are the number of hydrogen on neighboring environments. So for example, the proton for the alcohol, the red hydrogen, that looks to be a singlet, sort of doublet. Alcohol is going to be a little tricky. But with the carbon in the center of this molecule, the one where the alcohol group is attached, that has its hydrogen green, and it looks to be that we are looking at a quartet. So the n+1 rule means that the hydrogen of this carbon are neighboring an environment that has 3 hydrogens attached, which we see on the methyl group all the way at the end. Whereas that methyl group, the hydrogen blue, their resonance due to shielding around 1.2 parts per million. That triplet implies by the n+1 rule, triplet minus 1 would be the number of neighboring hydrogen, while the methyl group has a neighboring carbon with 2 hydrogen on it. So the triplet 3 minus 1 would be the neighboring hydrogen. And just to get further into shielding and deshielding, something that's further to the left, further downfield or higher parts per million, that's called deshielded, where anything that's closer to 0 parts per million or further to the right is more shielded, that is upfield. Now, not every type of spectrum uses coupling. Carbon NMR, if we were to include the coupling due to nuclear spin, that would cause messy spectra and would give hard to decipher information. Instead, what is used is broadband decoupled carbon NMR, or just C13 NMR. And that will let you see all the different unique carbon environments throughout your molecule. A way to enhance or to better elucidate the types of hydrogen environments could be by distinguishing them by the number of protons attached to those carbon environments. And that can be done through distortionless enhancement by polarization transfer, or depth NMR, which involves changing a polarizable angle, typically 45, 90, or 135 degrees, and different information will be obtained from the resulting spectra. For depth 45, essentially any carbon environment that has at least one proton attached will show up as a peak. Therefore, any peak that does not show up on our depth NMR but shows up on our broadband decoupled carbon 13 NMR, those would be for carbons without hydrogen. That could be a ketone carbon, a quaternary carbon, things like that. And for depth NMR, where we have a polarization angle of 90 degrees, that allows for revealing which peaks on the broadband decoupled spectra are specifically for carbons that only have one hydrogen attached. So depth 90, it should only show peaks for the carbon environments with one proton attached to that carbon environment. And then depth 135 gives a good range of information. 1, if a carbon has an odd number of protons attached, 1 or 3, then the carbon peak will show up positive or above the axis. Whereas if there's a carbon environment with 2 hydrogen attached, then it will show up as a negative peak. Therefore, we can further correlate all this information back to our original broadband decoupled spectrum and better isolate which carbon environments are for, say, functional groups that prevents having any hydrogen attached, or essentially when we expect to see maybe 1, 2, or 3 protons attached to specific carbon environments. And taking that information a step further, where depth NMR can help elucidate the types of carbon environments and specifically the number of protons attached to those carbon environments, it's also possible to perform coherence spectroscopy, or in this case, HSQC, which is heteronuclear single quantum correlation, or coherence nuclear magnetic resonance. It's a way of correlating information on 2 different NMR spectra. In this case, proton H1C13, HSQC. One of our axes is the proton NMR, and the other is a portion of our carbon NMR, specifically the carbon's environments that had protons attached. And this HSQC can let us see for the carbon environments that we were able to determine had either 1, 2, or 3 protons, methyls, methylenes, so on and so forth. It lets us know which peaks on the proton NMR are those attached protons correlated to. So depth can tell us which carbon peaks have 3, 2, and 1 hydrogens, and then correlating that through heteronuclear single quantum coherence spectroscopy allows us to say where those environments with 3 hydrogen, what's the proton peak correlated to those 3 hydrogen. For the proton environments that have 2 hydrogen, for the carbon environments that have 2 hydrogen, what peak or peaks on the proton NMR are those correlated to? And there are other forms of NMR as well. There's also N15 various types for phosphorus, boron, silicon, and likewise, perhaps the most useful type of HSQC would be H1N15, where that, along with H1C13, can be used for identifying proteins in biochemistry. And all this is made possible through the interactions of protons and electrons, nuclear spins, and electron spins in their half-integer spin magnitudes, which is possible when following Fermi-Dirac statistics.